Hello everyone. So in this video session, I will be talking about the Laplace correction to Newton's formula. In my previous video, I was trying to explain how to derive an expression for velocity of sound waves in gas medium. So whatever the formula we have arrived at, so that formula is V is equal to square root of K divided by rho. And then, so we have also discussed in the previous class that, or previous video, that velocity of sound waves. While deriving the velocity of sound waves in gas medium, Newton assumed the propagation of sound waves as an isothermal process. So based on that, he had showed that V is equal to square root of P by rho. So now we have calculated the velocity of sound waves by using Newton's formula as in the formula V is equal to square root of P by rho. If we substitute the value of pressure, that is 1 atmosphere at NTP, in SI units 1.013 into 10 power 5 Pascal, and density of gas 1.293 kg per meter cube. If we substitute these values in Newton's formula for velocity of sound in air or gas medium, we get the velocity as 280 meter per second. So but Newton himself has determined the velocity of sound waves in gas medium as 330 meter per second in its experiment. So therefore, there is a discrepancy between theoretical and experimental values of velocity of sound waves in gas medium. So this discrepancy was corrected by Laplace in 1814. So he suggested that the correction to Newton's formula by considering the following important facts, and they are: there is no heat exchange takes place during the compression and rarefaction, because compressions and rarefactions during the propagation of sound waves takes place so fast that there is no possibility of the sound the medium exchanging heat with the neighboring region of the medium. So that means whatever the heat generated at the compression region should be communicated to the rarefaction region. So that should happen very fast if at all temperature has to remain constant. So but what is happening in this case is, suppose if we consider sound waves of, let's say, 500 hertz, in 1 second there will be 500 number of compressions created and 500 number of rarefactions are created at a point. So that means, so 500 times in 1 second the compressions are forming. So the exchange of heat cannot be so fast. It cannot air cannot communicate heat to the surroundings, thereby its temperature will not remain constant. And another important fact we need to keep it in mind is, air is a bad conductor of heat. So therefore, so with these two arguments, the temperature, we can say that the temperature cannot remain constant during the propagation of sound waves. So therefore, based on these things, Laplace suggested that actually the propagation of sound waves in a gas medium is an adiabatic process. So now we know that for an adiabatic process, P into V power gamma is equal to constant. So where gamma is the ratio of specific heat capacities of the gas at constant pressure and constant volume. So therefore, differentiating that PV is equal to constant with respect to V, we get V power gamma into dP by dV plus P into gamma V power gamma minus 1 equal to 0. So now taking that first term to the right hand side, we get gamma P into V power gamma minus 1 equal to minus V power gamma into dP by dV. So now cross multiply that V power gamma minus 1, we get gamma P equal to minus V power gamma by V power gamma minus 1 into dP by dV. So now V power gamma divided by V power gamma minus 1 is equal to V. So therefore we get minus V into dP by dV, or it can be written as gamma P is equal to dP divided by, or minus dP divided by dV by V, where dP is nothing but the excess pressure acting over the section under consideration, and dV by V is the volume strain. So whatever the excess pressure is there, so that is the stress acting on the section, and dV by V represents the volume strain. So therefore, the stress by volume strain is the bulk modular. So therefore, in the formula which was derived by Newton, if we substitute gamma p for k, we get the velocity as v is equal to square root of gamma p by rho. So now substituting the values for gamma, p and rho at NTP, gamma is 1.42 for air medium at NTP. So therefore v is equal to square root of gamma p by rho. Gamma is 1.42, p is 1.013 into 10 power 5 Pascal, and rho, the density of air, is 1.293. So if we substitute all this and simplify, we get the velocity as 333.54 meter per second, which is very close to the experimental value of velocity of sound in air medium. So therefore, so this formula, or whatever the correction suggested by Laplace, the experimental value and theoretical value are agreeing with each other. Okay. Next, moving on to the next important concept, that is velocity of sound waves in a rod. So for that, this derivation is similar to what we have derived in the previous video session, that is the velocity of sound waves in a gas medium. So there we considered a tube of gas. Here we are considering a rod of certain area of cross section, let's say A. So let the axis of the rod be parallel to the x-axis along which the sound waves are actually traveling. So now in this rod, consider two sections like A and B. So these two plane sections of the rod are at distances x and x plus delta x from the arbitrary origin on the left side. So now when the sound waves propagate, so each and every layer of the, or each and every section of the rod will be displaced in the direction of propagation of sound waves. So let's say A is displaced to the position A dash and B is displaced to the position B dash. Suppose if y is the displacement of the layer A, then dy by dx represents the rate of change of displacement with the distance. So therefore, the displacement of the layer B or section B is y plus dy by dx into delta x. So dy by dx is the rate of change of displacement with distance, and delta x is the distance between the layers A and layer B. So therefore, the total displacement of the layer B or section B is y plus dy by dx into delta x. So now the new positions of A and B are, during the propagation of sound waves, A dash and B dash. So now the position of A dash is x plus y. Similarly, the position of B dash is x plus delta x plus y plus dy by dx into delta x. So now the length of the section of the rod between A and B, so that is before the propagation of sound waves. So whatever the length of the section between A and B is there, that is delta x. So now when sound waves propagate, as we have mentioned, as we have discussed just now, different layers of the rod will be displaced through different extents. So let the sections A and B be displaced to the positions A dash and B dash respectively, such that the displacement of A is AA dash, which is equal to y. Similarly, the displacement of the layer B or the section B is BB dash, which is equal to y plus dy by dx into delta x, where dy by dx is the rate of change of displacement with distance. Now the new length of the section AB is equal to delta x plus dy by dx into delta x. So this we get by subtracting the position of A from position of B during the propagation of sound waves. That is B dash, position of B dash minus position of A dash, we will get delta x plus dy by dx into delta x. So now the increase in length of the section of the rod between A and B is equal to the new length is delta x plus dy by dx into delta x minus the original length, that is delta x. So therefore we get increase in length as dy by dx into delta x. So now using this, you can write the longitudinal strain produced in the rod as dy by dx into delta x divided by delta x, which is equal to dy by dx. So this linear strain means the rod is elongated through a certain distance. So therefore, this linear strain will set up restoring forces within the material of the rod. So these restoring forces will try to bring that rod to the original configuration or to the original length. Suppose if F1 is the restoring force acting over the section A, then you can write the stress, linear stress, or it is also called as the tensile stress as F1 divided by A, where A is area of cross section of the rod. Suppose if Q is the Young's modulus of the material of the rod, then Q can be written as tensile stress by volume strain or linear stress by volume strain. Sorry, this is actually linear strain. There is a mistake in that. Tensile stress by linear strain equal to F1 divided by A divided by dy by dx, or F1 is equal to Q into A dy by dx. So this is the force acting on the section A of the rod. So now the force acting on the section B can be written as F2 is equal to F1 plus dF1 by dx into delta x, where dF1 by dx is nothing but the rate of change of force with distance, because all the layers of the rod will not be subjected to same amount of force. Suppose if we have considered the section A, B, now section A is subjected to a force, but B is subjected to a different force, and that force is identified in terms of the rate of change of force with distance. Therefore, F2 can be written as F1 plus an additional force dF1 by dx into delta x. So now the resultant force acting on the element or acting on the section between A and B, F is equal to F1 plus dF1 by dx into delta x, that is the force acting on the section B, minus F1, that is the force acting on the section A. If we take the difference between force acting on the section A and force acting on the section B, the resultant force gives us actually whatever the resultant force which is acting on the section AB. So therefore, that plus F1 and minus F1 cancels, we get F as dF1 by dx into delta x. So now substituting for F1 from the previous equation, that is from equation 3, we get F as d by dx of qa into dy by dx into delta x, or F is equal to qa into d square y by dx square into delta x. So now, so this force, this resultant force will produce an acceleration in the element of the rod between the layers A and B. So therefore, the net force acting on the section can also be written in terms of acceleration as F is equal to mass of the section AB into acceleration. Mass means its volume into density. Volume of the section will be delta x is the length and A is the area of cross section. Therefore, A into delta x gives us the volume into density, that is rho, the density of material of the rod. So therefore, delta x, A into rho gives us the mass, and d square y by dt square is the acceleration. So therefore, we get the force as delta x, A into rho d square y by dt square. This is the force acting on the section of the rod between A and B. And we have also written the force in the previous equation, that is the equation number 4. So now both these equations, equation 4 and equation 5, are representing the force acting on the section of the rod between the layers A and B. So now if we equate those two, on both sides we have A and delta x as common. You can cancel that, and if we take that rho to the left hand side, we get d square y by dt square as q by rho into d square y by dx square. So now this equation is of the form d square y by dt square equal to v square into d square y by dx square. So that is the differential equation of the wave. Comparing equation 6 with the differential equation of the wave, we get the velocity. If v is the velocity of sound waves in rod, then comparing those two equations, we get v square as q by rho, or v is equal to square root of q by rho. So therefore, from the above expression, it is clear that The velocity of sound in a metallic rod depends on density of the rod and also Young's modulus of the material of the rod. I hope you have understood whatever the concepts I tried to explain in this. If you come across any doubts regarding this, regarding the concepts which we have discussed in this video, you can post it in the comment section. I will try to answer those inquiries in the next video session. Thank you.